A very good evening to everyone. I welcome you all to this Institute lecture on the glue that binds us all. And the speaker who is going to deliver a talk on this such an interesting topic is Professor Raju Venugopalan. I request Professor Venugopalan to introduce today's speaker.
So, hi Anil, should I start now?
Yes, please.
Okay. So, welcome to Professor Raju Venugopalan. It's my privilege to introduce you. So, let me start it. Professor Raju Venugopalan was born in Kochi and then attended Belgaum Military School before finishing his schooling at Wilson College in Mumbai. Thereafter, he attended the University of Chicago on an undergraduate scholarship and received his PhD from Stony Brook in 1992. After postdoctoral fellowship at Minnesota, Seattle, and Copenhagen, he joined Brookhaven National Laboratory, BNL, in 1998, where he is currently a senior scientist, serving previously as group leader of the nuclear theory group from 2010 to 2015 and 2016 to 2021. He is also an adjunct professor at Stony Brook University and held the Excellence Initiative Chair of Theoretical Physics at Heidelberg University in 2015-16. He is a fellow of American Physical Society and was awarded the Humboldt Prize in 2016 for lifetime achievements. Back to physics, the vast bulk of visible matter in our universe exists due to nature's strong force, whose fundamental constituents are quarks and gluons. One of the great achievements in physics is the development of a successful quantum theory of strong force known as quantum chromodynamics, QCD, one of the four fundamental forces in nature. QCD is a theory of breathtaking simplicity on the surface, but containing multitudes of reaches within a deeper understanding which continues to elude us. Professor Venugopalan's work involves on how quantum states that generate the strongly interacting matter look like in nuclear wave functions, how their properties can be described as a color glass condensate, CGC, which is an effective theory of QCD at high energies. Color refers to a type of charge that quarks and gluons carry as a result of strong nuclear force, and the word glass is borrowed from the term for silica and other materials that are disordered and act like solids on a short time scale, but liquids on a long time scale. It's a matter of time scales. Professor Venugopalan, the co-author of the 1994 seminal paper on CGC, is listed as one of the 28 most influential papers published by Physical Review D in its 50 years history. Professor Venugopalan's work primarily on many-body emergent features of QCD, which is a quantum theory of strong interaction, has received over 27,000 citations. Again, coming back to physics, when two CGC color glass condensates collide, they shatter to form a highly non-equilibrium plasma state. In strong analogy with inflationary universe, quantum fluctuation play an essential role in thermalizing strongly interacting quark matter and in generating the long-range rapidity correlations. Remarkably, experiment at relativistic heavy ion collider in short RHEC at Brookhaven National Laboratory, USA, and Large Hadron Collider, Geneva, are able to extract fingerprints of such dynamics, providing insight into how strong color field thermalize into quark matter. The CGC can also be probed directly in deuterium gold collisions at RHEC and in proton nucleus collision at the Large Hadron Collider LHC. Further precision studies in the future are feasible with an electron ion collider. With The ongoing discoveries at RIC and at the LHC, active plans for future facilities, the study of collective phenomena in QCD, the most perfect theory known till date, is a vibrant subfield of theoretical physics. Now I humbly welcome Professor Raju Venugopalan to enthrall us on the topic, the glue that binds us all, nature's strong force and the origin of mass in the visible universe. Professor Venugopalan, I request you to start your talk.
Yeah, thank you very much for this extremely kind introduction. It's a real pleasure to be able to speak to you, at your colleagues and students at Roorkee. As Professor Patra mentioned in his talk, the topic of this lecture today is about the history of our origins in a very fundamental sense. Is that how the mass in the universe came to be, and that, as this scale denotes here on the slide, really merged from very collective many-body phenomena, which one usually associates with condensed matter physics, but also occurred in the strong force, as Professor Patra mentioned, which led to the creation of visible matter in the universe. And so what I'm going to talk about is a story of our origins, fundamentally, but how we can study it in very concrete ways and learn some of its extraordinary and breathtaking properties with high precision now, it turns out, that we're able to do. So as Professor Patra mentioned, this is one of the great achievements of physics in the 20th century and going into the 21st century. And I hope to be able to give you a small window into some of these ideas, which will hopefully help your thinking on some of these topics. So with that, let me go to my very first slide. And so the central player in the story is an object called the gluon. And as will become clear, this is a somewhat mysterious object still, in how it functions in our standard model of physics. So the standard model of physics is one of the great achievements of the late 20th century. And this is something that came to fruition over time through a succession of experiments and ideas, starting after World War II, which culminated in this theory in the 60s and 70s, 1960s and 70s. And so now our understanding is so clear of the standard model that you can see posters in physics department corridors with this following this chart that's shown here, which talks about the matter content of the standard model. What are the objects? What is the matter that makes up the standard model of physics? And what are the force carriers that transmit them? So you have matter and force carriers which transmit the forces, and these are the strong, the weak, and the electromagnetic forces. So so the carriers of the strong force are the quarks, which are listed here. So these are up, down, charm, strange, top, and bottom. And as you'll see, these I hope you can see on my slide here where my cursor is, this denotes a spin, the charge, and the mass of these objects. And the masses are in MeV units. That's mega electron volts. That's 10 to the 6 electron volts. And so the spin of all the quarks is spin 1/2, as you can see. But they have different charges. So the up, charm, and top quark have charges 2/3. So these are fractional charges compared to that of the electron. and the down, strange, and bottom quarks have charges -1/3. However, we see that there's a distinct pairing between light and heavy quarks. So you see the up and the down, and to some extent the strange quark are on the light side. Okay, so so the up quark has 2 MeV, 2.3 MeV. The down quark is 4.8 MeV, and the strange quark is about 100 MeV. While there's a big jump when you go to the charm quark, which is more than 10 times heavier than the strange quark, and then it goes even further to the bottom and strange quark. The strange quark is very massive. Okay? So if you think about the mass of the proton that makes up all the constituents of nuclei, protons and neutrons do, those objects weigh about 1 GeV, and so the top quark is 173 times the mass of the proton. And so this is the matter content of the standard model in terms of quarks in the sector that experiences the strong electromagnetic and weak forces. Now there are also objects called leptons, which interact via the electromagnetic and occasionally the weak force. And so these are the electron, which we're all familiar with. That's one reason I'm able to talk to you, is because of the motion of electrons. And so electron is fairly light. So to give you a sense, it's 500 kilo electron volts, or 0.5 MeV. So it's about half the mass of the up quark. So it has a charge, which is unity by definition. And then there's the spin. So the electrons are also spin 1/2 objects, as are its heavy partner, the muon, which is, again, strikingly, it's about 200 times heavier than the electron. And then there's a tau lepton, which is further 10 times or 15 times heavier than that of the muon. So these are so-called leptons, and they have also these objects you may have heard of, which have been in the news quite a bit, which are neutrinos, which are remarkable in the sense is that, so here, so they have no charge, as you can see, they're chargeless. They have spin 1/2. And what was striking, and one reason they're in the news, is that it was believed for a long time that they were possibly massless. And through a series of beautiful experiments, we've now discovered that they actually have masses, and there are bounds on their masses. So this is, again, so as I mentioned, the matter content of the standard model in terms of quarks and leptons. And so now coming to the force carriers, the photon is the reason you can see me, is the force carrier of the electromagnetic force, and it has 0 charge. It has spin 1, and it's massless. So that's a photon that we learn about. And then there are the other gauge bosons which transmit the weak force, which is responsible for radioactivity. And that's the Z boson and the W bosons. The Z boson is also chargeless. It carries spin 1, just like the photon does. And it's very heavy. Okay, so it's 90 GeV, so it's approximately 90 times the mass of the proton. And the W boson is somewhat lighter, but they come in ±1 charge variants. So they are charged objects. They carry electromagnetic charge. And they are also spin 1. Okay? So these are the objects that were transmitters of the strong, of the electromagnetic and weak forces. And then we come to the gluon, which is the topic of this lecture, which is also mass 0. So just like the photon, it doesn't carry any mass. It carries 0 charge, so it's 0 electromagnetic charge, and it carries spin. Okay, so it's a spin 1 object. So all these bosons are spin 1 objects, as you'll see. And so, sorry, the force carriers are called bosons because they carry integer value spin. while the quarks, which carry spin 1/2, are called fermions. So the matter content of the Standard Model is made up of fermions, and the force carriers are gauge bosons. Now, a great discovery in physics was the discovery of the Higgs boson. And the Higgs boson is quite massive. It's 126 GeV. And it has zero charge and spin. So it's a scalar object. It has no, doesn't carry any spin. And so this was the final missing chink in the Standard Model, which was filled by the Higgs boson, giving us a fairly complete picture of the strong electromagnetic and weak interactions. Now, conspicuous by its absence is the graviton, which is responsible for gravitational radiation and the gravitational force in nature. And so one of the big quests in physics is to try and understand how that fits in along with the Standard Model to have a unified theory of the strong electromagnetic weak forces and the gravitational force. Okay, so to construct a quantum theory of all of this would make our picture of our current universe more complete. Now, the gluons, which is the topic of this lecture, as I mentioned, are the force carriers of the strong force. They're massless, they carry spin 1, and they have no electromagnetic charge. So they're sort of this humble little object sitting in the corner of the table. And what I'm going to talk about is how they play a crucial role in giving mass to matter and some of their properties. Okay, I'm having some trouble changing slides. Okay, now, so how do we know that gluons exist? And so there were a series of experiments done. There were indirect hints for the existence of gluons from a number of experiments in the late 60s, starting in the late 60s and early 70s. And as I will mention, the theory that we're going to talk about, quantum chromodynamics, that Professor Patra alluded to, had gluons as its central component, but it was not clear whether these objects actually existed physically. There was no evidence for them until these experiments were done at what's called an electron-positron collider, where beams of electrons were scattered in beams of positrons, which are their oppositely charged partner. So it's the antimatter counterpart to electrons, which, when such beams are created and collided with electrons, annihilate into bursts of radiation. So this is a virtual photon representing that. And then occasionally these virtual photons, which are not on shell, they're virtual objects, they can decay into very energetic quarks and antiquarks. So quarks also interact with the electromagnetic force, as this diagram suggests. And so these quarks and antiquarks, then, they proceed along and fragment into a number of subatomic particles, which are represented as jets. So these are highly collimated streams of particles which carry energy and which are deposited back to back into this detectors shown here. So if you think about the beams of electrons and positrons meeting at this hole in the center, then the quarks and antiquarks are created there, and then they go along these trajectories here. And then these detectors, you'll see these back-to-back, sort of counts of energy that's being deposited in the detector, suggesting that such a process took place. And so this was known before experiments were done with electron-positron beams, that you could have such jets. But what was really striking was that this is the Tasso detector at the positron-electron ring accelerator in Germany, was that occasionally you would see so-called three-jet events, and that could be interpreted as the emission of a gluon from one of the jets. So you could have a quark come along, or antiquark, emit a gluon, And then this gluon would carry some energy, which would then fragment again into a bunch of subatomic particles, and you would get this third jet seen here. And so by looking at these patterns and understanding the likelihood of seeing such jets, you could deduce quite accurately that these were the objects that we were looking for, the fundamental objects in the standard model we call the gluons. And since these experiments were done in 1980, physics letters P, there have been subsequent experiments at electron-positron colliders, more powerful ones, later, more energetic collisions of electrons and positrons revealed that you can have 4 and 5 jet events, which very precisely reproduce the properties of theory that I'm going to talk about, of which a central component was the gluon. So, as I noted, gluons are massless, yet their dynamics, I'm going to argue, is responsible for nearly all the mass of visible matter. So the Higgs boson that we've heard of quite a bit, the God particle, is only responsible for the masses of the quarks. Okay, so that gives you a very elegant explanation of how the masses of the quarks came to be. However, the masses of the quarks, light quarks, as I noted to you, are much lighter than the mass of the proton and the neutron, which is what makes up nuclei and the matter of stars and galaxies and us. So how did these very light quarks, right, which are about 100th the mass of the proton, combined with massless gluons, create the mass of the proton? So this is the essential story of our origins, given a little push by the Higgs, but then it's the dynamics of the strong force between the quarks and the gluons, which then generates the mass of visible matter. And in a twist, the object that we call the God particle is actually seen most strikingly in experiments at the Large Hadron Collider that Professor Patra mentioned, where you have collisions of protons which then emit gluons, which then scatter and then produce the Higgs. So the gluons that I mentioned are a crucial element in actually studying the Higgs particle, and measuring its properties, because then the Higgs then decays into different final states. Here it's shown decaying into a bottom and anti-bottom quark. And so it's this humble gluon is responsible for us being able to measure the properties of the particle, which we believe gives mass to the quarks. So, okay, so this is to cut to the chase, we now have a modern theory of the strong force, and it's a quantum theory. So just like the development of a quantum theory of electricity and magnetism was called quantum electrodynamics. So that was one of the great achievements of the 20th century. Quantum chromodynamics is its counterpart for describing the strong force. And chromo means color, which is something that I will explain as I go along. So even though we have this beautiful, elegant theory that I'm going to talk about, which was first elucidated in a paper by Gell-Mann, Fritsch, and Leutwiler about 50 years ago, its origin was quite tortured, as many theories often are. In hindsight, they look very nice, but the way they are constructed and they come to be seems almost miraculous in retrospect. Just as the pupae of a caterpillar, sort of lets out this ugly object, which then goes into this beautiful butterfly. And similarly, the idea of QCD started in thinking about ways to categorize the zoo of subatomic particles that people were seeing in particle accelerators around the world, after World War II, they were seeing large numbers of subatomic particles being produced and decaying, and measuring them and trying to understand, what is it that unites them in some systematic way? Is there a symmetry, an underlying coherence to the patterns that they were seeing? And they were able to classify these particles into so-called mesons and baryons. And mesons, we now understand, are bound states of quarks and antiquarks. And baryons are bound states of three quarks. And so by inventing what he believed to be mathematical objects called quarks, Murray Gell-Mann was able to classify all these subatomic particles into what he called a so-called eightfold way. He was very influenced by Buddhist thinking. And in this way, he was able to explain, categorize in a kind of periodic table all the subatomic particles that they were seeing. A highlight of which was his prediction. So it's not just sufficient to categorize using new ideas, it's that you have to predict what some of their novel consequences could be. And Gell-Mann's great triumph was that he was able to say that, okay, if I have something called a strange quark, then I can have a combination of strange quarks which should exist. And this was the so-called omega minus. And this was discovered by my colleague Nick Samios at Brookhaven in experiments done with the bubble chamber there at the AGS accelerator. And that led to a Nobel Prize for Gell-Mann. Now, even despite the discovery of the omega minus, there was a lot of skepticism whether this object really existed or it was just a mathematical abstract construct. Are quarks real? Or are they just a mathematical shorthand? But some number of people started taking this idea seriously, and then they came through a very complex set of discussions and ideas over the next decade, which then led to the modern theory of quantum chromodynamics, and which I'm going to talk about. And so I'm going to explain some of these things that are listed here. So this was really what is called a lepidopteral metaphor that I'm talking about, is that the path to QCD, this beautiful object, went through a tortured and confusing set of discussions and ideas beforehand. So one thing perhaps to take away from our modern understanding of nature is this very simple idea that trying to understand patterns in nature in terms of symmetries is a very powerful way of thinking about nature. And this very straightforward statement was developed into a principle which, to the best of my knowledge, was first articulated by the Nobel laureate C.N. Yang, is that symmetries dictate interactions. So what is symmetry? Symmetry is an invariance under some property. So you rotate your coffee cup by 180 degrees, and then it looks exactly the same as if you didn't rotate it. And so the invariance under some kind of operation leads to conservation laws. And they're so-called global symmetries that you apply to all the objects in your cup. So when you rotate your cup, you're rotating all the elements of your cup by 180 degrees. And so these are essentially what give us the conservation laws of energy and momentum, and more sophisticated conservation laws, which then in quantum physics are characterized by selection rules and quantum numbers and so on. Now, a great development was in the 20th century was really driven by Einstein's theory of gravity. It was the idea of so-called gauge symmetries, that you can have local operations performed at each space-time point which satisfies a symmetry. And Yang's great insight is that such gauge symmetries actually tell you what the interactions are going to be. So it not only tells you about conservation laws, global properties, it also tells you about the local forces that act on objects in a particular theory. And so through this principle, you could understand the standard model, strong, weak, and electromagnetic force. And we also understand general relativity deeply in this way. As I mentioned, it came from general relativity. But of course, the great quest is still to unify all of these forces together. In fact, if you would permit me, there's a nice historical note, which is the precursor to quantum chromodynamics is so-called Yang-Mills theory. And the idea for Yang-Mills theory was discussed in a paper by Yang and Mills in 1954. So that's almost 70 years ago. And so here's C.N. Yang with Robert Mills, who was a graduate student then. And this was written at Brookhaven National Lab, where I am. And I would say this is perhaps the most important paper from BNL, because in its essence, this paper revolutionized physics as we know it. Okay. One could argue that it had almost the same great impact as Einstein's theory of general relativity does in our thinking of nature. And it was at that time very little understood and mostly ignored for nearly 2 decades before people realized that this is really the foundation how we should think about quantum field theory, which is the basis of our understanding of the standard model. And in fact, this Yang-Mills paper is stunningly modern if one reads it now in hindsight, because it could have been lifted from a textbook on quantum field theory, which was written more recently. And for instance, they define something called the field strength tensor. So this is the electric and magnetic fields in some tensor notation. And the B's are what we call gauge fields, or these are the gluon fields. So gluons are not just particle-like objects in quantum field theory. You have to think about them as space-time fields. And these gluons, so the photon, for example, can also be written in the same kind of equation for the electric and magnetic fields that we see in electromagnetism. But in electromagnetism, we don't have this additional term here, which is bilinear in the fields here. So this is B nu here, which in electromagnetism, you would not have such a term. You would just have these first 2 terms, which are linear in B. Yeah, so just derivatives of B with respect to space-time. So it's this non-linear term which is really crucially responsible for our existence. So these are so-called non-abelian self-couplings of gluons, which really create all the complexity of the strong force, and that is found in this equation 4 in the paper. Now, in physics, already at the undergraduate level, right, we learned that we can understand forces and fields through equations of motion, and these are obtained by taking extrema of so-called Lagrangians, which contain all the matter and force content. And so of the theory, and so in electromagnetism, for example, you would have such a term, F mu nu, which is basically the same F mu nu as shown here, but shown in some vector notation. And then there's a coupling of the matter fields, which are these psi's to the gluon field, and then there's a mass term here, okay, for the quarks that one has. So already in Yang-Mills' paper, they had all the features that we need for quantum chromodynamics, okay, but it was missing a very important ingredient, which is the idea that the self-coupling of gluons needs an additional charge. So gluons, unlike photons, carry a charge. Okay, so just like electrons carry a charge, quarks carry a charge, gluons also carry a charge, okay, which causes gluons to interact with each other. And so photons do not interact with each other. So if you see two beams of photons in a dusty room, they kind of go crisscross each other without interacting. While gluons won't. So if you see two beams of gluons interact, they will very strongly scatter each other. And so this word color is a whimsical word. So it's a different kind of charge from electromagnetic charge. And so this is a whimsically named object called color. It doesn't mean color in the sense of that we know it, but it's just a nice whimsical representation of the charge carried by gluons. And these objects then satisfy this gauge symmetry that I mentioned to you, which is a symmetry at each point in space-time. So these gluon fields at each point in space-time, the color charges that they carry satisfy a certain rotational symmetry in an internal space, which is given by the abelian group SU3. Okay, so you can think about this as a kind of rotation in some internal space, which seems very abstract, but also is very real at the same time because it has consequences. And so this is a paper that was written by Yoshiro Nambu and Moya Han. And Nambu is one of the great physicists of the 20th century. He was awarded the Nobel Prize for his contributions to theoretical physics, even though it was not explicitly acknowledged for this work. But he was very instrumental through his idea of color in the development of quantum chromodynamics. So, as Professor Patra mentioned, QCD is a nearly perfect fundamental theory of the quark and gluon fields that make up matter in the universe. And what do we mean by nearly perfect is that if you were to by hand set the masses of the quarks to 0, the theory would have no parameters at all. There would be nothing to tune or fix. Its predictions are what it would be. So it's the addition of quark masses, which are then given to us by the Higgs mechanism, which bring the only parameters into this theory. So it is in that sense nearly perfect. It's also nearly perfect in the sense that the theory is very rich in the symmetries that I mentioned, which, as Yang noted, dictate interactions. So it has this classification of symmetries, which I don't expect everyone to to follow, but just to give you a sense of what these are. So there's this gauge color symmetry. And as I will mention, that this symmetry is preserved strongly by quantum chromodynamics. And then the QCD Lagrangian that I gave you a hint of in the previous slide, which dictates the equations of motion, have something called a chiral symmetry, handedness, which is exact for massless quarks. And it's a global symmetry, just like when you rotate your teacup, that is satisfied by all points in space-time equally. So that is something called an SU3 symmetry for left and right-handed quarks that is exact. And then there are symmetries having to do with the conservation of the number of baryons, baryon number of the quarks, saying that you have a fixed baryon number, say for the proton or the neutron. And likewise, there's also an axial charge symmetry for massless quarks. And then there are additional symmetries in QCD which have to do with scale invariance. So if you scale spatially the quark and gluon fields, the equations of motion are invariant. And likewise, there's charge, parity, and time reversal symmetries. So there's a very rich set of symmetries in QCD. Now, all of these symmetries, with the exception of the color symmetry, are broken by properties of the vacuum. So it is in QCD that we first start to see that the object that we call the vacuum, the zero energy state, naively, has profound properties which are not contained necessarily in the equations of motion of the theory. And this was the most striking example of such theories that people had postulated, that you can have a very complex vacuum state that has properties which are not visible in writing down the equations of motion. And so all of these symmetries, the chiral, axial, scale, and discrete symmetries can be broken by vacuum and quantum effects. And these give rise to the very complex phenomena of the strong force. So it's not just the existence of symmetries, but the patterns by which such symmetries are broken in nature that lead to phenomena that we can observe. So one of the goals in physics is to understand phenomena in terms of broken symmetries of some underlying simple coherent theory that describes how this pattern emerges. So inherent in QCD are the deepest aspects of relativistic quantum field theories. Okay, and these are some of the objects that I'm going to talk to you about briefly: confinement, asymptotic freedom, and so on. So let me go to this remarkable phenomenon that QCD describes, which is called asymptotic freedom. So if you remember, early on, I showed you the slide where you had the scattering of two electrons, which annihilate into a photon, which goes into quark-antiquark jets. But now imagine that these quarks can scatter of each other. And the way they do so is by emitting a gluon. So the gluons are the force carriers of the strong force, while the quarks, at least naively, are the matter contents, right? The spin 1/2 objects that I mentioned. While the gluons are spin 1 objects, so the quarks emit a gluon. Now, since this is a quantum theory, the gluon can temporarily, for a short period of time, fluctuate into a pair of quarks and antiquarks, which then reannihilate to form a gluon, which then rescatters. Okay, such processes are allowed in quantum physics, where for very short periods of time, these objects, you can produce many such pairs of quark-antiquark pairs in this scattering. So this is again a reflection that the vacuum of the theory is very non-trivial. For very short periods of time, it can contain lots of energy, which influences the interactions between quarks. And similarly, but now the difference, so this is very much like in electrodynamics, where the photon could sort of scatter, could produce a pair of electrons and positrons and then go back into a photon in the scattering. But in QCD, a gluon, because it carries this color charge and has this nonlinear interaction that I showed you, can split into a pair of gluons now. And then these gluons can recombine to then scatter off the quark. So this is a kind of screening phenomenon where these quarks and antiquarks screen the scattering of these two quarks from each other. So it screens the force between them that's being carried by the gluons. While this, the gluon interaction anti-screens this, so it works against the screening mechanism that one sees. And the combination of them leads to a force as represented by the coupling. So the coupling is the strength of the force that's being exchanged between these quarks. And what this coupling shows you is that the coupling is not constant. So in electrodynamics, when we work with Maxwell's equations and in undergraduate classes in engineering and physics, the coupling constant is kept as a fixed object because it's in quantum electrodynamics, it's very weakly dependent on the energy or the resolution scale of the scattering. Not so in QCD. In QCD, the coupling is a very strong function of the distance or the momentum exchange in quantum physics, which is conjugate to that, the distance. So for the more energetic the energy carried by the gluons, that's represented by Q, the coupling actually gets weaker. So the more energetic the momentum carried by the gluons in the scattering, the coupling gets weaker and weaker, and it does so as a logarithmic function. So the solid line is a logarithmic function. And you see beautifully that this coupling lies on this. So in other words, when two quarks scatter at very short relative distances from each other, they're non-interacting. But as you try to pull them apart, the interaction between the quarks gets stronger. So this was really an absolutely stunning thing that really shocked a lot of people. And there were experiments being done which were indicating that, but people didn't believe those experiments because this was such a shocking thing. Because in the theory of electrodynamics, two electrons scatter more strongly when they're close to each other than they're far apart, right? So, I mean, electrons are very strongly interact. So if you take two magnets, for example, they're very strong when they're close to each other, but and so on. So, but the interactions between electrons get weaker as they're further apart. This is completely the opposite phenomenon. And so so the people who discovered this, Gross, Wilczek, and Politzer, Frank Wilczek was a student of David Gross at that time. They got the Nobel Prize for this, for showing that the self-interaction of color-charged gluons is fundamentally responsible for this property of asymptotic freedom, which means that asymptotic freedom means that, when they get very close to each other, they are free. So very large momentum transfers, very energetic gluons, they essentially are non-interacting. Okay? So quarks are non-interacting with each other. But as you pull them apart, they get more strong interaction. So this is a fundamental feature of quantum chromodynamics. Now, the reverse was also a striking phenomenon, is that when you try to pull two quarks apart from each other, and that's represented by this figure here of two quarks being, so this is an actual representation of the force fields between two quarks as you try to pull them apart. And the force between them gets stronger and stronger, as represented by this plot here. So this represents the potential, the force between two quarks as a function of the distance between them. And so at very short distances, it behaves like the Coulomb force of electromagnetism. But as you try to pull the quarks apart, the potential, the force between them gets stronger and stronger, and it's linear. In fact, two quarks will experience a force of about 16 ton weight. So these quarks are objects which have the size which we know to be less than 10 to the 18 meters. Right? So it's very, very small objects. Okay, but when you pull them apart to a distance of 1 Fermi, which is 10 to the minus 15 meters, okay, which is 1/billionth the size of a strand of your hair, these experience a force of 16 ton weight. Okay? So that's how strong this force is. In fact, you can think about these quarks as having a kind of string tension. So think of a rod that's connecting them, a string that's between them, which is fairly rigid. It has a string tension that is the sigma. And so you can think now of the mesons that we see in nature as bound states of these simple quark-antiquark pairs. So as I mentioned, mesons, baryons are the objects that we see in experiments, and they can be understood in terms of the underlying quark degrees of freedom as such kind of rigid rotators, if you like. And this gives us an intuitive picture of the confinement of quarks. And if you plot the spin of these mesons as a function of their mass, which can be rewritten in terms of the string tension here, it has this kind of linear trajectory, which seems to suggest this kind of picture. Now, in detail, we know that this picture is not quite right. Strings can break. They can produce pairs of quark-antiquark pairs. It's a more complicated picture. But magically, this kind of simple picture in terms of the stringy objects, which are kind of rotating and which have a linear potential, is somehow deeply true. Okay. Now, I mentioned these two ideas, which was the having to do with color, and that was asymptotic freedom, right? The self-screening of gluons, which interact with each other. And its converse that of asymptotic freedom is that when quarks, you try to pull them apart, They're very strongly interacting, and so much so that they experience this big, 16-ton weight, the distance of one Fermi, or 10 to the minus 15 meter. Now, there's another very interesting property of QCD, and it looks a little wonky and mathematical at the outset, but it turns out to be deeply profound, which is that quarks have a certain handedness. So you can split them up into left-handed and right-handed quarks, okay? Just as shown by this cartoon here. And so if the quarks were massless, you could literally write down this Lagrangian, which tells you the equations of motion of quarks, in terms of a Lagrangian for the left-handed and right-handed quarks in the presence of these gluon fields. But it turns out that even if the quarks were massless, this would no longer be true, because there's a remarkable mechanism whereby the vacuum plays a big role. And what it does is that the properties of the vacuum force the left-handed quarks to talk to the right-handed quarks. So that's represented by this kind of Mexican hat potential, which is that if you write down the Lagrangian as being just like a parabolic kind of potential, there's a phenomenon called spontaneous symmetry breaking, which tells you that at some point in the evolution of the universe, right, if you change the temperature of the universe, this symmetry that you had, that this parabolic kind of potential that the quarks lived in, would suddenly become this Mexican hat kind of shape. And then it would have to choose one of the two vacua that it would have to live in. And this tells you that the symmetry that you had between of left-handed and right-handed quarks, that they separately rotated from each other without knowing about each other, would no longer be true, and they would be paired. And so what this tells us, now it turns out that the fact that the quarks actually carry some mass, the up and down quarks, also does matter, because it tilts this Mexican hat in a particular direction, which forces them to choose one of the different potentials. But this mechanism together, which is called the Nambu-Boson mechanism, creates what is called a condensate, whereby the vacuum carries a certain amount of energy, okay, which comes from pairing the anti-right-handed quarks with left-handed quarks and vice versa. Okay. So there's a non-trivial chiral condensate in the theory which breaks this chiral symmetry. So the fundamental Lagrangian without quark masses had a certain symmetry, which is this handedness between left and right-handed quarks. They exist as if they don't know about each other, but the breaking of the symmetry spontaneously generates a certain amount of energy which forces them to pair with each other, giving energy to the vacuum. And it's this mechanism which actually takes these humble light quarks and converts them into the very massive protons that we know, which we are made up of. So what I'm describing to you on this slide is the reason why we exist. There's also another kind of symmetry breaking having to do with part of this chiral symmetry, which is a quantum effect in addition to a vacuum effect. It's called an anomaly, but I don't have the time to go into that here. So here's the essential mystery. Nearly all of visible matter in the universe is made up of colored quarks and gluons, but quarks and gluons are not visible. So rather than being a bug, it's a feature of the theory. They're confined into colorless hadrons, which are these mesons and baryons. So they're quark, antiquark mesons and baryons. All strongly interacting matter in the universe is an emergent consequence of this many-body quark-gluon dynamics. So the mass and spins of these hadrons, including protons and neutrons, arise from these massless gluons and nearly massless quarks. And there's still an elegance and a simplicity to the way nature organizes the properties of these objects, which we don't understand fully, even though we have what we believe to be the correct theory of fit. So this might seem a bit ironical, that is, we have a theory which we claim is the fundamental theory of nature's strong force, a pillar of the standard model, but we don't fully understand it. And there's a good reason for it, as I'll come to, and there's a reason why we believe it's the right theory, as I'll also come to. But truly understanding the essence of this mystery demands that we develop a deep and varied knowledge of all this emergent dynamics. So it's not something that would come from one aha moment where we say, okay, it is this mechanism, but the complexity of the theory is such that we need to probe and prod it in different ways. So let me now come to the power and the glory of QCD as represented by this beautiful butterfly. So why do we believe that QCD is the correct theory? So what we can do is we have these equations of motion of the theory, and we can put them, even though it's a nonlinear theory, you can say, well, so what? We have very powerful computers. Okay? We can put this on a computer and solve it. And indeed, that was the idea that came up with, was originated primarily with a physicist called Ken Wilson. And here he's sitting in a room, which he's holding an object called a telephone, which some of you may recognize, with a cord. And behind him are what were our computers. So these were state-of-the-art computers at that time, in the early 70s. And so Ken Wilson came with this brilliant idea that not only can you solve QCD by putting it on some kind of a lattice, a cubic lattice, to represent the spatial and time degrees of freedom of these gluon and quark fields, that this lattice actually gave us a deep way of thinking about the theory itself, because all quantum field theories have these objects called infinities. When you calculate these diagrams describing the quantum motions, you find that things blow up when you do these calculations, and then you have to reorganize those diagrams in a certain way that you get reasonable, sensible results. And this was already known to Feynman and Schwinger and people who came up with quantum electrodynamics as a feature of that theory, but it's also true in QCD. And what Ken Wilson realized is that not only does it help you to solve the equations of motion numerically by putting it on a big lattice, but it also gives you a way of thinking about fundamentally about what a quantum field theory means. Now, so what Ken Wilson's program has led to a first principles treatment. So you can take QCD, put it on the lattice, and solve it. And this gives us the properties of static properties of theory, masses, the magnetic moments, thermodynamics, so the pressure, the temperature, energy density as a function of temperature, and even chemical potentials in the theory. Now, when it comes to describing things like scattering phenomena, when if you take, say, a gluon and scatter it off a bunch of gluons, then the theory gets very complex for technical reasons. It's still a formidable computational problem. So if you want to say, okay, let me take two nuclei and then shatter them on each other, as Professor Patra mentioned briefly, then that problem is almost impossibly difficult right now to solve on a computer starting from quantum chromodynamics. Okay? So it's very challenging for what we call dynamical processes. But it's extremely powerful in actually doing certain things, okay, which tell us that we are on the right track. Now, of course, computers are very, very powerful now. So this is Summit built by IBM. And this is really, it has operations that are so fast that they are 200 petaflops per second, okay? About 1 million times faster than a typical laptop that I'm using. But now we also have gone further, and there's a new machine called Aurora that's coming on, that'll be at Argonne National Lab, which is really going into the exaflop regime. Okay, so it's going, you have even much faster computers to do such calculations, which were absolutely necessary for the results that I'm showing. So here's a plot of the masses in QCD of of the different mesons and baryons that I mentioned, which are calculated by putting QCD on a lattice and looking at larger and larger lattices and trying to carefully take care of these problematic infinities that I mentioned. And you see that with a couple of inputs of the masses of the pions and kaons, which are subatomic particles most abundant, in nature, you see that you can predict in red the masses. So these are the red are the predictions from the computer. And these, with one additional mass of a baryon that you give as an input, you can actually very precisely get the masses of the other particles in the zoo of subatomic particles that I mentioned at the start of my talk. So this was already 13 years ago. And then people have gone much further since, is that now you can put both QCD and QED simultaneously on computers. And you can use them to study not only the masses of the different mesons and baryons, you can also study mass differences, okay, between these. And so, for instance, this is the mass difference between, say, the proton and the neutron, which is primarily, the difference between them is due to the electromagnetic force. It's not due to the strong force primarily. And so because the mass differences are quite small, they are in MeVs, a few MeVs, while if you saw in the previous plot, they were, sorry, I don't know how to go back. Okay, in the previous plot, they are in the GeV range. Okay, so they're thousands of MeVs, while in this plot, they're in the few MeV range. And so again, these experiments can very precisely, these lattice numerical experiments very precisely agree with observations of these mass differences. Now, the other reason we believe that QCD is a correct theory, so that was what I showed you is a real triumph of solving QCD exactly on a computer with no additional parameters besides that of the quark masses given to us by the Higgs mechanism, and cranking it out, right, by just solving it by brute force. Now, if you recall, I mentioned this property of asymptotic freedom, where at sufficiently high energies of the gluons, sufficiently high momenta, the couplings between these gluons becomes weak. And if the couplings between gluons become weak, you can use a technique called perturbation theory, where you can systematically expand the calculations of scatterings and powers of the coupling. And since the coupling is very small, you can do it systematically to very high orders. So you can do it to some leading order in the coupling, next to leading orders, so this alpha s squared, and so on. And so you can actually look at, say, if you want to measure the probability or the cross section for seeing a Higgs particle at the LHC, you can actually calculate that using QCD primarily, because the Higgs is produced from gluons in this particular channel. And you see that with precision experiments, you can actually get to where the data are. And so this is a real triumph, and you see that there's a systematic improvement in decreasing the uncertainties to the actual physical value. And now people have gone to next to leading order in perturbation theory. So it gets more and more complicated. You have many more diagrams that you're computing in perturbation theory, but we are able to do it now and with precision make comparisons with experiments. So this is another aspect of the triumph of QCD. So even though QCD is extremely successful, there's still a lot that we don't understand of QCD. So if I plot the scattering in QCD in terms of the resolution and the density of particles that we produce in QCD, the hadron spectrum that I talked to you about is sitting here, okay, in this plane of scattering. While quarks and gluons at very high resolution that I mentioned, where we can see, say, compute the properties of the Higgs boson, or the likelihood we would see it, are sitting here. The rest is mostly terra incognita from first principles in QCD. Okay. And so this is where we're going. We want to understand how quarks and gluons interact strongly and create the kind of many-body physics that we know from condensed matter physics. So in condensed matter physics, what we study is emergent phenomena from strongly correlated electrons and photons interacting with them in many dimensions and so on. And so a similar kind of pattern also occurs in QCD, where you have strong many-body interactions between quarks and gluons, which are then responsible fundamentally for all this phenomena of confinement and chiral symmetry breaking that I mentioned to you earlier, which then create all the stuff that we observe in these experiments at collider energies, where you collide beams of protons or electrons with each other. And so there's also a regime of very high density gluon matter that I'm going to talk to you about, which sits on this edge when the coupling is either very weak or very strong, which gives us possibly some insight into all this many-body physics. So the many open questions that we still have about the QCD structure of matter, what is the three-dimensional quark-gluon structure, the proton, many-body correlations, and how thermalization occurs, and so on. At this stage, Binoy and Anil, I'm quite a bit behind. So how should we organize this? How much more time do I have?
You want 5 more minutes time?
Okay, so I've really quite a bit of my talk left to go. But I was going very slowly. But I can try and wrap it up. In maybe 10 minutes. Is that okay?
Fine. You please go ahead.
Okay.
Yeah.
Okay. So I was going very slowly, so I am very far behind in my talk. But I hope I've been giving you a bit of a flavor. So let me talk now about the many body features of QCD. So one way to understand this is through so-called deeply inelastic scattering experiments, electron scatter of, say, protons at very high momentum transfers, where the virtual photon now probes into the quarks inside the proton. And by doing so, you see that the proton is really not just made up of 3 quarks, but it's accompanied by a whole zoo of lots of gluons and quark antiquark pairs, which we call C-quarks. So if you look at the number distribution of objects inside the proton, which is this XF on the y-axis, as a function of the momentum fraction carried by each of these constituents, you see that there's tens of gluons and C-quarks inside the proton. So the proton is a very complex many-body object. So one way to understand this is the following. So imagine that you have a proton that's going along with some, you're taking the proton and the 3 quarks are carrying most of its energy. And in quantum physics, these objects are dressed by so-called quantum fluctuations. So the proton can emit a gluon, which can then get reabsorbed, or gluons can interact with each other, and so on. It's a very complex many-body system, which makes up the proton and gives it its mass. But now if you boost the proton to very high energies, so then what happens is that these gluons, they start to live longer and longer. Okay? This is Einstein's time dilation, because objects, when you boost them, they appear to live longer and longer to an observer. And so instead of seeing these gluons be reabsorbed back into the quarks, they start to live longer and longer on the time scale of an observer who's trying to look at that. Okay? And so an observer that's looking at it with very high momentum resolution at very short distances will see a large number of these gluons. And the process whereby the number of gluons increases is a function of the energy with which the proton is moving. So the higher the energy, the more such fluctuations will become visible. So you'll be lifting the veil underneath the hood of the proton. And then with the very, it's like, standing with a net and looking at a bunch of fireflies flicker in the night. And then the faster you're moving towards them at close to the speed of light, you catch more and more of these fireflies in your net, which otherwise would flicker into the night. And so longer-lived gluons radiate more and more longer-lived gluons. And this is a Markovian process, not unlike COVID, which generates a power law growth in the number of gluons. Okay, and it's a power law, not an exponential, because the number grows with a logarithm. And so what you get is a kind of boosted popcorn machine. So if you think of gluons as being filling up the pot, which is a proton, as you go to higher and higher energies, you're starting to see more and more gluons. And then you start to worry whether the lid of the proton can be blown off. Can matter become unstable? Now, it turns out that that is not the case, okay? And the nature has a way of regulating it. And what that means is that that's saying that the probability of the scattering of a probe, so imagine you have a virtual photon that splits into a quark and an antiquark, and this is what then scatters of the gluons inside the proton. And the gluons start becoming denser and denser as you increase the energy of the interaction. But there's a limit to how dense this can get. Okay, and that limit is said that the maximum probability for the scattering is unity. Okay, this is what is called unitarity. And so because of this, that actually imposes a strong constraint on the interactions between the gluons, such that the probability of their scattering, a direct hit, does not exceed unity. And simultaneously, the theory also tells us that if you start packing more and more gluons, so as you boost the proton to higher and higher energies, the gluons start living longer and longer and self-interacting with each other very strongly, there's the number of gluons that you can pack into any phase space area inside the proton. So per unit momentum, per unit area is maximal. Okay, so you can't pack more than a certain amount. And that condition, and that's required for the stability of matter, that condition creates an emergent scale, which is called a saturation scale. And this scale can be really quite large, and that comes from the screening and recombination of these gluon charges. Okay? And what that does is that this intensely quantum process where you have these fluctuating objects in and out of the vacuum around the quarks can be described as a classical object. It becomes a macroscopic quantum state, okay, which behaves like a classical field. And so this is kind of a remarkable property of classicalization. And so the picture that you get is that in the landscape is that if you have scatterings where on the y-axis you have the boost, so you have very high energy boost, so you boost the proton to higher and higher energies, and then you start looking at it with finer and finer resolutions, what you see is that the proton, no matter how fine a resolution you started with initially, you start producing more and more gluons and it becomes very dense. Okay? But then there's a maximum density for any given resolution, and that's what the saturation scale is. Okay, so you have some maximum size of these objects for any given resolution as you increase the energy. So this is this very many-body classical objects that you create as a result of this very quantum dynamics inside the proton. And there's some nice evidence for this. Since I don't have time, I won't go into it. And so this is what is the color glass condensate that Professor Patra mentioned at the start, is that it's very hard from first principles in QCD to compute the properties of this very strongly interacting many-body state. So it's a bit like in condensed matter physics. In condensed matter physics, you don't start with a QED Lagrangian and derive the properties of graphene, right, the strongly correlated electron system. What you do is you construct an effective theory which captures all the correct symmetries of the theory, which is appropriate for that energy that we're probing the system. And that tells you then what the properties of graphene are. And so similarly in QCD, you can construct an effective theory, and that's this color glass condensate, which captures the very non-trivial recombination and screening phenomena of these many-body gluon state, which is then this color glass condensate. So it's an effective field theory of classical quarks and gluons, which are then coupled to these gluon fields. Okay, so it's color, which is self-evident. The gluons carry color charge. It's a glass. because the time scales over which these very fast quarks live is much more time dilated compared to that of the lifetime of the more energetic gluons that they produce. Okay? And it's a condensate because these gluons multiply very strongly, and at some point they have a maximal occupancy, which goes as 1 over their coupling strength, which is characteristic of a condensate. Okay, so this is the color glass condensate. So I'm really way behind, so I should kind of move on. So I wanted to talk about how this creates, how you, in scatterings, when you collide two color glass condensates, you create the quark-gluon plasma. So this is a nice visual by the Nobel laureate T.D. Lee, where it says nuclei as heavy as bulls through collisions generate new states of matter. And this is what happens is that in a heavy ion collision, what you do is when you collide matter, you heat it up to temperatures which are 100,000 times hotter than the center of the sun. Okay, so the temperature is about 2 trillion degrees Kelvin in these heavy ion collisions. But it lives for a very, very short period of time, which then decays into producing lots of particles. Okay, and one of the issues that you may have heard about is that this matter then forms a quark-gluon plasma. And one of the big questions is that, how such a highly non-equilibrium state in the collision of this color glass condensates goes through some very non-trivial non-equilibrium process and then finally produces a state of thermal equilibrium, which is then this quark-gluon plasma. So what is this thermalization process? And in the heavy ion collision, you have some deposition of matter, which then gives you some momentum distribution, which then goes into the particles that you produce in this collider. So I don't have time to go into this. So I have reviews of modern physics from which you can find in the archive, which is published this year. We describe the very non-trivial, complicated process in which you have the space-time evolution of a heavy ion collision informing the quark-gluon plasma. And this has a phenomenon which is very remarkable. The system doesn't just go directly to thermal equilibrium, but it goes via something called a non-thermal fixed point. So there's a very non-trivial interplay between scatterings of the gluons, which are being collided in the collision of two heavy ions, and the rapid expansion of the system, which leads to something called a non-thermal fixed point, which is some universal property which is self-similar. And that's very similar to the phenomenon of turbulence, that weak wave turbulence that we know in statistical physics. And here's a very nice ditty which says that from bigger worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So the way you create such a fluid, which is the quark-gluon plasma with its very low viscosity per entropy ratio, is through such a phenomenon of weak wave turbulence in the early stages of the heavy ion collision. This matter remarkably turns out to be universal to cold atomic gases. So if you study the properties of this turbulence in producing the quark-gluon plasma, the self-similar behavior of that is very similar to that of a superfluid Bose gas. In fact, it's identical. The properties of one can be mapped onto the other. And so this is some remarkable universality that we observe between the world's hottest and the coldest fluids, which is something that I'd be glad to talk to anyone about more. And now there are experiments being done with these cold atoms which show such self-similar behavior. So these are rubidium atoms, which are in a Bose-Einstein condensate in an optical trap. And when you study their properties, it turns out that their distributions have this kind of self-similar property, just like that of the quark-gluon plasma. And so what we can do is, in this color glass effective theory, we can follow the properties of a heavy ion collision all the way till thermal equilibrium. So it goes through some kind of non-thermal fixed point, which has universal properties, and we can actually calculate from first principles in terms of this close packing scale, the saturation scale, what the thermalization time and the temperature are. Okay, so this is really remarkable that, such a complex many-body system can be followed all the way through to very good approximation, and one can calculate what the thermalization time and the temperature are for the system. And you find that if you go to sufficiently high energies, because the coupling only decreases logarithmically as QS, the thermalization time really goes to zero as you go to higher and higher energies. So at very, very high energies, in the collisions of nuclei, you have almost instantaneous thermalization relative to the lifetimes of the nucleus. So there's a very interesting correspondence between black holes and the CGC, which is really quite remarkable, between objects which are 1 billion kilometers in size as opposed to 10 to the minus 19 kilometers. And if you're interested, I have a paper with Gia Dwali which discusses this at length, but I'm very sorry I'm out of time, so I will kind of skip this part and just mention that now we have the ability to study QCD quite precisely through a machine that we're building at Brookhaven National Lab. So the structure of matter has had a long history by looking at shorter and shorter distance scales using more and more sophisticated objects, starting from light microscopes, which looked at cells and molecules with more precision. And then you started going into electron microscopes, which can actually look at much, much smaller distances of wavelengths and resolution in terms of tens of nanometers of smaller. And then to go even further, we invented these electron accelerators, which can look at distance scales of Fermi, so 10 to the minus 15 meters, and even smaller, so 0.1 Fermis. And then I talked to you briefly about this Hera collider, where we learned about the properties of quarks and gluons, that there are lots of quarks and gluons inside protons and nuclei. And these are now able to look at distance scales which are 0.001 Fermi, so 10 to the minus 18 meters inside the proton. So this is really quite a remarkable feat that we're able to study matter at such fine resolutions, at such short distances inside us. And so we are now building a very powerful femtoscope, the electron line collider. This is a $2 billion machine that has been approved for construction at Brookhaven. First collisions are expected in 2030 or so. And what this is going to do is going to use a Rick accelerator complex where you'll have an electron ring and a ring for protons and ions, heavy ions. And the protons will be up to 275 GeV. The nuclei are about 100 GeV, and they're going to collide at different intersection points. And there are these detectors that are being built and which will study with great precision the three-dimensional structure of quarks and gluons inside protons. So we'll be able to construct images in momentum of the distribution of, say, up quarks inside a proton or down quarks inside a proton, and also be able to understand spatially what their distribution is inside the protons and nuclei. Okay, so this is really going to give us a precision spatial tomography of quark and gluon distributions inside matter. And so what we can then do is really get down to the heart of the matter, is where did we come from with very high precision by trying to understand fundamentally the origin of nucleon mass, the origin of nucleon spins. This phenomenon of gluon saturation that I mentioned, where you have close packing of gluons inside protons and nuclei. And finally, the 3D tomography of where these quarks and gluons sit inside the protons and nuclei in spatially and in momentum. Okay, so thank you very much for your indulgence. And I'll end with this slide, which summarizes some of my talk, it's a Scientific American article that we wrote in 2015, so it's a little bit dated, but it's still fairly relevant, I think. And so if any of you are interested, please take a look. And the title of the article is "The Glue That Binds Us All." So thank you very much for your indulgence.
Yeah, thank you so much, Professor Raju Venugopalan, for taking us into the world of gluons. Thank you so much. Now the session is open for some comments, queries. So either you may post your queries in the chat box, or you can unmute yourself and ask the questions to the speaker.
Yeah, so I can't see the chat box. So if you could, if there are any questions in the chat, it would be great if you could relay them, or people can
Right.
unmute. Yeah.
Hi, Professor Gorishetty, can I ask a couple of things?
Yes,
This
please.
is Alok here.
Please.
Okay. Thank you, Professor Venugopalan, for a great talk. I just had a few things to ask. In particular, I'm very curious about this CGC black hole correspondence, because I have interest in gauge gravity duality for several years. I've been interested in this. So that's one of the things that I wanted to ask. And fortunately, I would say that you were not able to cover it in your talk. So anything that you say was going to be new.
Yes.
So,
yeah.
And if you wish, I can rattle off my two other queries, or they could follow with the kind permission of Professor Gorishetty, whatever way it works.
Okay, so thank you very much for asking this question. I truly appreciate it, because I had to really run through this since I ran out of time. So indeed, this is something. This is a somewhat novel idea, which is very recent, and this is based on my work with Professor Gyadwali in Munich. And so we suggest that there's a deep correspondence between the properties of black holes and that of these color glass condensates. And this comes from work by Gyadwali and his collaborators that he's been carrying out for almost a decade, where he has argued that black holes in general, which in general relativity are understood as classical macroscopic objects with geometric and thermodynamic properties, can be understood in his picture as very highly occupied. So these are, for example, a solar mass black hole with an occupancy of 10 to the 66. So you can think about these as very highly occupied but leaky bound states of soft gravitons. And with this kind of understanding and taking appropriate semi-classical limits of very high occupancy and taking LP to 0 and N to infinity, such a way that the Schwarzschild radius is finite, he's able to understand all of these properties of black holes, which were sort of considered to be very mysterious, the event horizon, thermodynamics, the No-Hair theorem, and so on, in a very simple kind of picture, quantum picture of black holes and black hole scattering. And so, for example, you could compute the black hole evaporation rate by a simple thermal rate with high occupancy, which then gives you something that's proportional to Hawking temperature, and you can recover the Hawking formula for this in this fashion, and also explains black holes as metastable states, which are not in equilibrium strictly, but are effectively in equilibrium because their lifetimes are long, given by very long occupancies. So the nub of it is that the same kind of logic that goes into thinking about bound states of gluons at very high energies inside the proton, where you have this maximal occupancy, can really be mapped onto this portrait of black holes, as highly occupied graviton states. And in fact, both of them saturate the Bekenstein bound. So of course, in the case of black holes, that's a Hawking, that's the Bekenstein-Hawking formula, area law. And one can show, and we show it in this paper, if you're interested, that such an area law is also saturated by the color glass condensate. And then there's other such correspondences between the two systems where you can really make a concrete map between the two in terms of understanding their evolution. So you can, for example, construct something like the page curve that we know in the evolution and decay of black holes. The problem is we're only able to take it a certain way, and then beyond the page time, so to speak, where the semi-classical description of black holes breaks down, that we are not able to follow in the black hole case. At least he's not able to follow it. And in QCD also, there's a more subtle understanding in terms of the quark-gluon plasma. So there is a certain correspondence between the two, and which we believe is exact at the point of unitarity. So it's classicalization and unitarity in the two pictures that we believe to be universal. So in the sense that for these states at maximal occupancy, you can't tell the difference between gravitons and gluons as strongly bound states. So this is it's a not necessarily a conventional picture, but it's something that hopefully will interest people like yourselves in this topic.
Just one quick question. I'm sorry if
of course,
yeah. Am I allowed to follow us, Professor Gorishetty, or am I hogging on the time?
Yeah, please, you can go ahead.
Okay, so I see this, but since this is very unfamiliar to me, I mean, so usually when you talk about gauge gravity duality, there is a sense of sort of a large N expansion, and you talk about corrections to the large N expansion by maybe invoking hydroderivative terms and the gravity equivalent, yada yada. But so here, what is the N that you write? I mean, I see there is an N
so this is very different from the usual gauge gravity duality. So it's really it's not a duality in that same sense. So here N is the occupancy. So essentially the idea is that, so if you think in terms of, say, Transplanckian scattering of gravitons, so think in terms of Transplanckian scattering of gravitons in the high energy limit or radial limit, where you produce a very high abundance of gravitons. And the claim is that you can understand black holes as metastable states of these very high occupancy of gravitons. So there is a kind of correspondence. It's related more to this kind of double copy correspondence that you may have heard of between QCD and gravity, where you can map QCD amplitudes into gravity amplitudes. And this would be, so the claim is that the CGC would be kind of the classic, or black holes would be the classical double copy of the CGC in that correspondence. So this N is really occupancy. And there's a similar kind of 1 over N understanding, but it's very different from the N, say in number of colors, for example, expansion. So it's a qualitatively different correspondence and interpretation of black hole physics.
It was quite intriguing. While you were speaking, I came to know when you mentioned your paper, I quickly Googled it, and it was very intriguing not to find a black hole metric in the paper. So usually, so apparently the claim is it's valid for a very large class of black holes and not for a specific type, it seems.
Right, exactly. So this is, so I mean, of course, we only look at, we're only looking at what you would call Schwarzschild black holes in this context, but I think the ideas can be generalized.
And the other intriguing thing was that this is non-supersymmetric, which is already a huge deal in gauge gravity duality.
So the
leap of faith, actually.
Right. So the statement here is that there is, so we're talking about Einstein gravity, so real black holes in our universe, not in 10-dimensional space-time. And we're talking about QCD. So we are postulating a correspondence between certain states in QCD, which are very short-lived, only accessible at very high energies, and with black holes in Einstein gravity. And this is, and in particular, in terms of their creation and Transplanckian scattering. So if you're interested, I strongly recommend also looking at these other papers by Dwali and his collaborators. So he's been pursuing this perspective for over a decade now. So it's difficult for me to just summarize it in a few lines.
All right, thanks. I had a couple of other things to ask, but I'll shut up and I'll wait for others, and then maybe you can circle back to me.
Yeah, if there are no other questions, I'll be happy to entertain them as well. Yeah.
Professor Ajay Singh has a question, I think.
Yeah, Professor Venugopalan, very interesting talk. And I request the Institute lecture series that one more talk, which will be complementary to it, should also be organized, because Professor could not complete thoroughly, and the major concluding part is remaining. So this was the first. And my one small question.
Yeah.
Professor Venugopal, I'm a condensed matter theory person works on many-body aspect, where I was observing many things which are actually very challenging nowadays in material also. When you go in nanostructure or in a you can say subatomic angstrom regime, so things are very different than the bulk solid state. So one thing I was just asking out of curiosity, you have charge to mass, then can we have mass to spin and then charge to spin ratio?
So when, as I mentioned very briefly at the start of my talk, the mass to spin ratio is deeply profound in QCD. So these lie on so-called radiate trajectories. So you find that you produce a large number of these, mesons and baryons, and they can be. So if you look at their masses and you study them on a plot with their spins, you find that they lie on these linear trajectories. And so we can we understand them to some extent, but somehow the actual phenomenon seems simpler than what our more complicated theory is telling us. But they tell you very much about. So I had this very simple picture, if you remember, of a rigid rotor, right? So you have a quark-antiquark pair, and you think of that as a rigid rotor that's kind of rotating. And you can think of these different spin states as arising from that. But
different angular momentum states,
yeah, and so exactly, and so that's now with regard to a deeper understanding of the other things that you mentioned, one of the big challenges for us is really to construct a 3D picture of the proton as a many-body state. So you can think of these quarks and gluons as having think of them as orbiting inside the proton, and they have their own spins, but they also have orbital motion. And the question is, how does that generate the spin 1/2 of the proton? Okay, so each of them has these spins, and so you want to understand what is the contribution from the spins of the quarks, what is the contribution of the spins of the gluons, what's the contribution from their orbital motion. So these are things that we're still trying to fully understand, and that's why we want to build this electron ion collider, because it can take 3D pictures, so it can do tomography, just like you do in condensed matter physics at some level. So it's of course,
because this is a very appealing question nowadays. That how to just like thermal transport. So how spin degree of freedom contribute to thermal transport? Because if you look at the usual solid state physics, there are U and N processes. It is the U process which contribute thermal conductivity, not N. So how it happened with the spin, which are bosons, when they transport through a nanostructure or a very small, say 1D tunnel or a point, then how it will contribute to the phase and thermal current is still a very in solid state also in nanostructure, a very appealing and interesting.
Right. So as Professor Patra can also elucidate separately to you, is that there are similar kinds of questions now in these heavy ion experiments where people try to understand how the angular momentum that these ions contribute to the formation of the quark gluon plasma leads to very non-trivial vortex structures, okay, which transmit spins across large distance scales and give you some kind of global polarization of these quark gluon states. So there are similar sets of questions, many body questions that one can address in QCD, but we are, far behind our condensed matter colleagues in kind of in some ways, because these are not tabletop experiments that we can do. So we have to infer such things from looking at very complicated final states in experiments.
Okay.
Yeah.
Thank you, Professor Kopp.
Sure.
Yeah. So thank you, Mr. Raju.
Thank you.
Now is the time for vote of thanks. I request Professor G.D. Verma, head of the physics department.
Professor Mishra had some questions, but I can also take it offline with him, or of course, time's getting late there. So it's up to you.
I think Anil, I think we please allow Alok to ask question if Professor Venugopalan has no problem.
Of course not. Yeah, I'd be happy to speak as long as necessary.
Okay, please. Professor Alok, please continue.
Thank you so much. So I'll be very brief. I just had two curiosities.
Right.
So the first curiosity is G-2. What is the story there as of now? And because I think Brookhaven BNL was one of the places where about 2 decades ago this experiment was probably done to a very large degree of precision. So I just wanted to know what is the current status of that, because I'm not a phenomenologist. So I want to, that's the first question. And the second question is again a curiosity, which is that in the strings community for many years now, so there's been this story about essentially initiated by Witten, which is the use of twistors in calculation of perturbative amplitudes and maximum helicity violating amplitudes. And then there is this story of the amplitude hedron program of Nima Orkani Hamid. So I just was wondering that the QCD folks, I mean, do they actually use these, or I mean, how quote unquote popular are these with them? That's my second curiosity.
Let me start with your second question, if I may, because that's one that's actually close to my heart, because that's something I'm actually working on. So what I've been, so I actually have a paper with Andy Strominger and his students on somehow importing some of these ideas of asymptotic symmetries from gravity into QCD. And again, there, as we argue in our paper, we find that there's a very powerful role played by the CGC, actually. So there's a color memory effect in QCD, which is exactly analogous to the gravitational memory effect that you have in understanding gravitational scattering, right? So Strominger has this program there. But more deeply also, I think, these Bern crossover rules that came from, which is very strongly related to this amplitude program, actually, you could argue helped initiate it, are exactly analogous to a word-line formulation of quantum field theory, as Strassler showed. And I've been using that very strongly in my work, actually. So I use these ideas, for example, to argue that the chiral anomaly plays a deep role in the spin of the proton. I have a paper on that. And I'm also thinking in terms of how to use these in terms of efficient computations in QCD. So to answer your question briefly, the answer is yes, it is very powerful and very useful, but it's only starting to make its impact in many body physics along the lines that I talked about. So it has been used to compute, say, amplitudes of the LHC and so on, that people are trying to do that. But in terms of the kinds of many-body phenomena, there are just a few papers, which I've also been working on. Now, coming to your second question, yes, the mu and G-2 experiments were done at Brookhaven it was really pioneered by Vernon Hughes and Lee Roberts at Brookhaven. And when the Brookhaven experiment ended, there was a 3 sigma deviation between the predictions of the standard model and the experiments. And then the experiment was dismantled and it was moved to Fermilab. So that's an interesting story in itself. And then the experiment was completely redone, and they found that their results agreed exactly with the Brookhaven experiment. Okay, so there is still, there's some changes in the error bars, but it's essentially the same 3 sigma discrepancy. And so the question really is why? And so you could say it's beyond the standard model physics. There could be some novel physics. There have been thousands of papers written on that. But it could also be a QCD effect due to our imperfect understanding of the hadronic matrix elements. So there have been lattice calculations that have been done. And there's, in fact, a lattice consortium which has gotten together and kind of established common discussion, parameters and so on. And they came out saying that, they still find this 3 sigma discrepancy. However, there's one group that claims that, including the lattice effects, they can explain the 3 sigma. So whether there's beyond the standard model physics from G-2 is still, I would say, under some debate, and unfortunately, it's not settled.
Thank you.
Thank you. Any more queries from the participants? Yeah, if there are no queries, I request Professor J.D. Verma, the head of the physics department, to deliver a vote of thanks.
Thank you, Professor Gaurisetti. So, good evening to all. On behalf of the Institute Lecture Committee and also on behalf of Physics Department, I sincerely thank Professor Raju Venugopalan for delivering a wonderful talk. We look forward to your personal visit to our campus when the situation becomes normal. I thank Professor B.K. Patra for playing an active role in organizing this lecture. I thank all the participants who joined through WebEx and YouTube Live. The Institute looks forward to your active participation in upcoming lectures. Thank you all for making this event successful. Thank you.
Thank you very much for inviting me, and it was really a pleasure to talk to all of you. I apologize I went severely over time.
No, not at all.
That's not uncommonly the case, but I look forward to meeting all of you and talking to you more. And I would welcome questions people may have. If they want to send it to me by email or otherwise, I would be glad to answer any questions.
Great. So thank you once again, Professor Raju Venugopalan, for spending your valuable time. Fine. So now,
Okay, good night.
the event
Thank
is,
you.
yeah.
Okay.
So the event is closed with this lecture.
Okay.
Yeah.
Okay,
Thank you.
goodbye. Thank you. Bye.
Okay, Patraji,